All right, so here we go. So we have this triangular truss that we're working with. We have 100 pounds being applied to the right and 60 degrees, so a nice equilateral triangle. 100 inches on this one, so being equilateral. All the other ones are 100 inches. Yeah, this is kind of participatory. All right, fixed point here, and then we have rolling joint on the other side. The modulus, 1 times 10 to the 6th psi. Area of each segment is 0.1 inches squared for an EA of 100,000 pounds. And then a length of each one, as we said, 100 inches. So we want to find the displacement of each node, support reactions, and the stresses in each element. So that's what we're going to solve for here. All right, here we go. So here's the process. Remember this. So we got pre-processing. We've got to determine the nodes and elements. All right, so there are nodes and elements. We're going to put node 1, bottom left, node 2 in the right, node 3 up top, and element 1, 2, 3. So I'm going to draw some on the board. Because we're going to reference back to this. You guys have it on your hand now. We won't see the slide, but it's going to be nice to reference back to. The shapes are just done to kind of signify nodes versus elements. Typically, I'll try to do that, circles versus squares, but really it's just to highlight one versus the other. All right, now we need to get the angles. The angles are very important because they show up in that transformation matrix. All right, so if you look at element 1, all right, so here's element 1. It consists of node 1 and node 2. And what we're going to say is, hey, node I is 1 and node J is 2. So if we go from 1 to node 2, that angle, with 1 being the pivot point, is equal to 0 degrees. So if we do it from that horizontal going up, it's 0 degrees. All right. We go to element 2. All right, we got element 2 is made up of node 2 and node 3. And again, we start from horizontal and we work our way over. So we go 90, 120. All right. So that's how we get the angle for node 2. And then node 3 is 1 and 3. We could have done 3 and 1, which we'll go back and I'll show you how we can do that as well there. But if we go 1 to 3, again, we start from horizontal, work up, and we get to 60 degrees there. All right, so that's how you figure out the angles, all right, based on the node locations. All right, number 2, we want to assume a solution that approximates behavior of an element. All right, so we kind of set this up already. We're saying, hey, our K value, our stiffness is going to be AE over L. All right, AE we know is 100,000 pounds over 100 inches, the length. So the K value for each element is going to be 1,000 pounds per inch. Now this could change if you had different lengths, right, or different stiffnesses or different areas. But in our case, they're all the same. But it could change. All right, so let's do this part. So we're going to go over to Mathcad. I have to scroll all the way to the top because it's open in the middle of it. Okay, so we have the stiffness already in there, 1 times 10 to the 6th, 0.1, 100 inches. And if we scroll down, all right, we have AE over L. Right, we said that was AE over L. Okay, and what's the value of it? 1,000. All right, so let's hit equals on that. I'm not getting 1,000. You guys getting 1,000? Oh, hey, look there. There's a nice little note. Look at that. All right, so yeah, backspace out that kilograms per second and type in pound force, LBF, divided by inches, and then enter. All right. So what you're going to find is sometimes the units are going to be great. They're going to work out well. That's one of Mathcad's beauties of maintaining units throughout, and you don't have to worry about conversion as much. Sometimes it won't work out. So as much as you can, use it, but then you're going to find at some points when you're going into matrices and you're doing some things that can't maintain the units. But for most cases that we're doing right now, it will. All right, so we've got that part, sir. Okay, so let's go back. We got our 1,000. All right, so we're going to develop the equations for our elements. All right, and we got to the point where we took the transformation matrix, multiplied times the global stiffness, times the inverse of the transformation matrix, and it gave us this. This is the global coordinate system version of our stiffness matrix. Right? So we want to do this. That's how we got it, right? So we want to do this for element 1. All we have to do is put in theta is equal to 0 degrees. Right? Because over here that stiffness value is the same for all of them, that K value. All right? So we're going to put theta is equal to 0 degrees. All right? So that would become this guy. So we'd have 1 and -1, etc. For element 2, again we said that was 120 degrees for the theta. So we put that in and we get this guy. And we do the same thing for element 3 and we get this guy. All right? But you're not content to just see it on a slide. You want to do it. All right, so let's do it. All right, so we come back in here. So we have the transformation matrix. So what I've done is I've already defined it. Now, there's no values there. It's just A, just in a blank A. The way Mathcad used to work is that if you wanted to get a particular value from this equation or from this matrix, you'd have to have A defined above it. Now, there's a function now where you can put A anywhere in the spreadsheet and fix it, and it'll use it anywhere. But typically, it always had to be above the equation before it could be used below. All right? So what we're doing here is kind of along that line. So this equation, there's no values for it. You can hit equals next to it, and you're not going to get anything because A hasn't been defined. All right? So that's fine, because what we're going to do is we're going to do these down below. These are areas. So you can see I can collapse this and expand it. These are areas. If you want to use these are under, remember here, calculate, no, document. Yeah, so document right here. This is grayed out because I'm in an area right now, so I can't put an area within an area. But what's nice about it is that you can put lots of stuff into it, and then you can collapse it, right, and keep working. And kind of maybe, once you know your calculation's working in one area, you can close it up and kind of maybe see things before it and after it a little bit better. All right, so let's go into element 1. All right, so A is going to be our angle. So what's our angle going to be for element 1? 0. All right, so you can see what am I doing right there. What's this whole pi over 80? Yeah, so I'm just converting from degrees to radians. So I want in radians here. All right, T1. All right, what's T1 going to be? So this is my transformation matrix, so I need to transform. And I've already have it up here, really, is this guy right here. This is T as a function of A. So I just need to call that. So I'm going to call T as a function of A. Now A is defined right here, right? We just defined it. Right? So if I had equals on this guy, I get my 1, 1, 1, 1, 1 matrix, identity matrix, essentially. And then now down here for my stiffness matrix, I need to put in my transformation. I need to transform, going back up here, I want to transform my stiffness matrix K into my global stiffness. So capital K global, right? Let's type it in. It's going to be our T1 times our K matrix times K times, you can do it either way. You can do the transform of it or the inverse. I'll do the inverse here because they're the same. And oh no. All right. Inverse, yeah, for matrix. For matrices, yeah. Do something else. Yeah. What's that? Yeah. Matrices aren't clean like that. All right, so we got that for element 1. All right, so I'm going to close that up. We'll go to element 2. What's element's 2 angle? 120. All right. And then for T2, we're going to put in T as a function of A equals. All right. So what happened here is that, again, we redefined A. So A was defined up above, but since we redefined it here, this overrode what we had for A in element 1. So Mathcad only takes the most local A that shows up to the equation. All right. So now for the to get the global coordinates, we need to do our T2 times our K times our T2, and this time I'll do the transpose of it. I think we can change the unit system. Let's see if that'll work. All right, so the question here is, can we change the unit system? And we could try over here. Oh, you guys can't see drop-down menus. Here's the units again, up here on the toolbar. This is under Math tab, units. And once you click on the unit tab, you should see units, SI. And I believe it should be the second one down, might help us out with that. So we can see what happens now with element 3. So we go to element 3. Which angle? What do we got for element 3? 60 degrees. All right. And T3 is going to be T as a function of A. And then our stiffness value there, that's kind of cheating over the page here. Let me go down here. So we got T3 times K times T3 inverse. Inverse. Yeah, so what happened there is, so here's, if you see, I changed the unit system. This isn't right because this is pound mass. All right, so you still have to change it anyway. So unfortunately, in this case, you're going to have to stick with, well, you could stick with that if you want to. You still have to change it either way. So. All right. Well, good. So now we have the global coordinate system, but it's still in the local form, right? This thing is still only looking at just one element. So let's go back here and go a little bit further here. All right. So what we developed is this guy right here. We have the local form, but global coordinates. Why is it the local form? Because it's only looking at the nodes 1 for element 3. So look at the element 3 on the board. It's only looking at node 1 and node 3. Node 2 is not showing up in here. All our matrices right now are 4x4s. We want them to be 6x6. We need to have node 1, 2, and 3 in the x and y directions. All right, so to get from our local form to our global form, we need to multiply by a transpose matrix. All right, we need to transpose it. So here would be 1, 2, 3, 4, 5, 6. We're going to have 6 different rows and only 4 columns. All right, those columns represent I and J for a particular case. All right. So again, if we focus just on element 3, we can do it this way. Where if you say I is equal to 1 and J is equal to 3, here's I is 1, right? So I is node 1, and so IY is node 1Y, and J is 3, node 3, so we got to go JX down here to 3X, and JY down to 3Y. Now you might be asking yourself, what if we switched them? Fantastic question, because that's the next one. All right. So if we said I is equal to 3 and J is equal to 1, now we go IX is going to be 3X, so now the 1's down here, and IY is going to be 3Y, so the other one's down here. All right. See how they flip-flopped? And 1's up here with JX and JY. All right. So that's how you figure out where to position them within the matrix. All right. So again, note that the theta Right? If we say I is 1 and j is 3, like we did, theta is 60. But if we say that 3 is I and 1 is j, what's theta now? Yeah, you got to take it from here and all the way around. You got to take it negative from here. That way to curve. So you get basically I point is your pivot point, or without you determining. So we're going to do this. Remind me if I forget it, but we're going to keep going through. But we'll come back to this and show you that it doesn't matter which direction, as long as you're consistent with how you apply the angle, it'll still come out the same. All right, so let's do that. So we'll go back to Mathcad here. All right, so we're trying to, here we go. So if note the parenthetical statement here. So this is the global coordinates, local form, and we're going to shift to global coordinates, global form. All right, that's what these sections are all about. All right, so let's open that up. All right, so I said we're going to have a 6x4. So let's put in our 6x4. I showed you one way that we can go in matrices and insert matrix. That might be the quickest way right now, but I'll show you this way as well. I believe if you put a square bracket in there, it starts to create it. And if we have element 1 consists of what two nodes? Element 1 consists of, it's on the board, 1 and 2. All right, so we need to put, which one is node I and which one's node J? 1 is I and 2 is J, right? All right, so let's do that. So if it's gonna have a 1 in the first. Let me do this the second way. Anyway, let's delete that back. I'll do it this way on the next one. This one's not gonna be as clear. All right, so come up here. Let's go insert matrix, and you're gonna have to do it on your own because you're not gonna be able to see this. But we want to make it a 6x4, and have that come in. All right. So if this is UIX and this is UIY, this is U2, U2, U3, U3. This is going to be a 1, and then you got zeros everywhere else. So I can just arrow key around my matrix after I put in the values. All right. What about this next row? What do we have here? Do you have anything here? Or is this all zeros? What? Got a 1 right here? So 1 and then 0 everywhere else? No, not a dash. 0. All right, what about here? Do we have anything? All right. Because this row and the next row have to do with node 2. So, yep. So we have that guy, and then 0 everything else. And then 1. And so note that node 3 doesn't show up here. We're putting zeros where node 3 would be, but that's fine because node 3 isn't part of element 1. All right. So now we're going to want to find our global form. All right. What are we going to do here? We're going to take our local form and get it to global form. What are we going to do with the local matrix that we had up? Now this is for element 3, but it's the same thing for element 1. What are we going to do to this guy? K-1, right, to get it to our global form. This is a 4x4. This is a 6x4. You know, trans 1, right? This guy right here, times, what's that? Thank you. Now let's see what happens if I forget it. K sub 1, right? Because that's this matrix up here. Again, for element 1, not element 3. Here, maybe close them up. This should be easier. There's element 1 right here. This guy right here. Times trans 1 transpose of that. All right. Go ahead and hit equals on that. All right, so that's what happened here. So I forgot the S. So variable is undefined. So I just go in here and add my S back in. Yeah, so let's look at that. So here's the question is, if we have trans 1, you can't take the inverse of a non-square matrix. Right? And we got to change units on this guy as well. All right. So everybody good there? All right, so see if you can do element 2 on your own. I'm not saying mine's right, by the way. All right, who wants to take a crack at it? Zeros in the first 2 columns. Rows. So I got zeros in the first 2 rows. Why? Okay, there's no node 1. In element 2, there is no node 1's not in there. So yeah, so we got zeros for the first 2 rows. And what do we got for the last 4? One here. So 1, 1, and then 1, 1. So why is that? So 2 is node I. So I is in the first 2 columns. And 3 is node J. J is in the second 2 columns. So we got to give 1s for the 3 and 1s for the 2. All right. And this is the same over here. Yeah. So let me go back here. Because see how this is I and this is J? For element 2, we have no node 1. So this says element, this is node 1, this is node 1, so this should be all zeros in these first 2 rows. Because node 2 is where we said, hey, we're picking a pivot point from there, it's going to be 120 based on that. Then we have to have a 1 here and a 1 here. And 3, because it's node J, it would be 1 and 1 just like this one is. Right. And then I think I have to go to a different view here to change my units. All right, and then element 3 you should be able to do. We just talked about that one. And I don't know if you saw me when I did. So you could do square bracket, and you type in your numbers. And if you hit tab after you type the number, you'll add a row. And if you hit a shift space, you add a column. If you forget, like I did, go to the Matrices tab and hover over one of these things, and you'll get the shortcut for one of these inserts. All right. Any questions there? Shift space. Again, also, I forgot to. So if you go up to the Matrices Tables tab, the ribbon, and then just hover over that item, it'll say what it is. All right, so we have them all in the global form now. So now we can assemble them all. We take the global form, global coordinates of our element 1, element 2, and element 3. We sum them together. We can get the global for all of our things combined together. All right, so element 1 is going to show up there because it can consist of just nodes 1 and node 2. Element 2 is going to show up down here because it consists of just nodes 2 and nodes 3. Notice the purple in the middle, red and blue. That was my wife's job. Element 3, you ready for this? What's element 3 made of? 1 and 3. 1 and 1 and 3. But 1 and 3 and 3 by itself. So now it shows, and we got green because blue and yellow, right? And orange is yellow and red. Yes. So, all right, so a little crazy there, but that's how it shows up in those different spots there. All right, it's in color on your handout too. It's printed in black and white. All right, but if you want to see that, it's on. It'll be on the video, and then also this presentation's online. All right, so let's do it. It won't be nearly as cool and colorful in our case because we're just going to open this guy up. And our overall stiffness, we're going to take our kg, ones that we just created, so kg underscore 1 plus kg underscore 2 plus kg underscore 3. Don't hit equals on that one because it'll go off the page, which is kind of too late because the other ones did. But if you do it on the next one, then you can get this guy, and then again, you got to change units. All right, so pretty straightforward there.
So maybe
Yep. Yeah, because what we did here is see how this one it turned out. Here's values, values, zeros, and zeros, values, values. So this is the same way that we just put it in here, right? All the yellow stuff, boom, 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 right? Comes from this, 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 and this. So that's how it shows up there. All right, so you should come up with that final form. So 1.25 times 1,000 right? Yeah, I think you have 1.25 times 10 to the third in our case. All right, running out of time here, so I'll keep going. All right, so we got to apply the boundary conditions. On your handout, I don't have what's coming up here, so if you want to put lines on it, you're going to have to do it manually. All right, we're saying we have no displacement at node 1 in the x direction. All right, so that's going to take out the first row in the first column. All right, you're going to have to put those lines in if you want them. There's no displacement in the y direction at node 1 either. That was a fixed point there. So that's going to take out the second row in the second column. And then we also had a boundary condition of what? Node, which direction? Y direction. So that's going to take out what and what? Row and column number. Yep, look over here. So row 2, 2y, right? So it's going to take out row 4 and column 4. All right, now you can do that on paper really easy, right? And you can rewrite it and you'll be done. We want to do this mathematically, legitimately, honestly. Some other word that ends in "ly." All right. We also have a force we need to apply. We have that 100 pounds being applied at node 3 in the x direction. So our load matrix is going to look like this, all right? Zeros and then 100 pounds there. All right. So let's look at that. So there's the 100 pounds. All right, but we want to reduce this guy down. We want to apply these boundary conditions to reduce this guy down based on our zeros. So how do we do this? Here we go. We need to create a boundary condition matrix that keeps only the things that aren't knocked out because of zero displacement. All right, so node 1, x and y direction, and node 2 in the y direction are all zeros. Right, and we're only going to keep information about node 2 in the x direction, node 3 in the x and y directions. Okay? So that's why the placement of each one of those. And so those three columns become U2x, U3x, and U3y. All right. Now we need to take this and multiply this times our global stiffness matrix. So let's go do that in Mathcad. Well, let's see the results of it. So once we apply this to our global stiffness equation, it's going to reduce down to this, a 3 by 3. All right. And we're going to reduce our force matrix down to this 3 by 1. All right, so if we solve it ultimately, then we'll get these displacements. So let's go do that. All right, so let's scroll down here. So we got to apply boundary conditions. All right, so we have the boundary condition matrix. We only want to keep U2x and U3x, U3y. So let's create our matrix there. So it's going to be a 6 by 3. And we got zeros in the first two rows. 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1. Right. And the way we're going to reduce our global stiffness matrix is take the boundary condition matrix, take the transpose of that, because this is a 6 by 3, and we're going to multiply it into a 6 by 6. So 6 by 3 into a 6 by 6 doesn't work. So we actually have to transpose it first. So we're going to transpose it, so now it's a 3 by 6. Right? Times our global stiffness matrix, and then times our boundary condition matrix non-transposed. Whoops, without the minus sign. To get this guy. All right, so now we have the reduced form of our stiffness matrix. And we need to do the same thing with our force matrix. So we need the global force matrix. We don't have that yet. We have to create it. So that's the 0, 0, 0, 0, 100, 0. We're going to reduce that guy too. So we're going to take the transpose of the boundary condition matrix times our global force matrix we just created. I'm going to add back here on the force, global force matrix, add the units there. Come out a little bit more cleanly there. All right, so now that we've reduced them, we've reduced our stiffness matrix. We applied the boundary conditions. We have the force being applied. So down here in the solution phase, we're going to put those in there. So we want the final displacements. So we're going to take our kg reduced, which we just created right here, up above. We take the inverse of that, times our reduced force matrix, which we just created. And if we get it in inches, all right, we have the same thing we had over here, if we believe the PowerPoint slide. All right, so 0.05 inches, 0.225 inches, negative 0.0144 inches. All right. Now we want to maybe go back, and we want to inflate it so it's not the reduced matrix, but it's got all the displacements in it. So we're going to go backwards using the boundary condition matrix again. So boundary condition times our reduced displacement matrix, and correcting units is this. All right. So there we can see we have 0.05 inches, 0.225, negative 0.014, and then 0 at the 3 places where we had the boundary conditions that said they needed to be 0. All right. For the reactions, this came from mainly last time, but we can take the global stiffness matrix times our global displacements, and then subtract off the force matrix, and that'll give us the reactions. What are the reactions at each node? All right, and if we do that, we should come up with this. So let's do that in our Mathcad file here. So go to the next area there. So we're going to type in that equation. So we have our global stiffness matrix, our non-reduced global displacement minus the global force matrix. And correcting units. It's not the same thing. What's wrong? If you go back, it's 100, 86, 0, 86, 0, 0. We got 100, 86, 3, 86, 1.2, and 3.1. All right, so they're essentially 0. It's 10 to the minus 14, 10 to the minus 15. So this is an artifact of what you're solving for in the solving process. So those can be taken to 0. All right, so we're out of time here. But as we can follow the rest of the way through, it talks about how you can take it back and solve for the forces within the, the forces and the stresses within each member. This is probably the biggest thing to highlight right here. This is going to be different than the book the way I have it presented. I do it so that when the stress comes out, if it's positive, it's the tension. If the stress value is negative, it's in compression. So what you're used to seeing, but the book had it flip-flop. So just heads up with that. All right, everything else will be pretty straightforward. It has the solutions here, so you can try to do it with Mathcad. Whew. All right, and see if you come up with the same results. All right, I'll post this video if I went a little too fast in some spots, and that'll give you the chance to catch up. All right. Yeah.
Can you go over how you chose boundary conditions?